Today's last speaker is Marco Zambon from Leuven, and he will speak on singular subalgebroids and their integration.
Thank you very much, David, for introduction, and thank you to the three organizers. So I will talk, so the word Poisson will not appear in the talk, unfortunately, but I will talk about something very closely related to the algebroid and the groupoids, which are very relevant for Poisson geometry. And I understand that in the school, these objects were treated, so I will not define them at all. So I will assume that they're known. So this is based on working, well, partially in progress with my collaborator, Jakubos Androulidakis. And let me start with something, well, relatively well known. So integration of Lie subalgebroids. So when I mean Lie subalgebroids over the whole base manifold, so I call them wide Lie subalgebroids. Okay. And actually, all along the talk, so let me fix some notation. I will fix a Lie algebroid A over M. So this be a Lie algebroid. And assume that it's integrable, and fix an integrating, well, source-connected Lie groupoid. So fix G integrating A. Okay, so the theorem I am referring to is the theorem by Moerdijk, Moerdijk, and Bursztyn from 2006. And it starts the following. So it's about wide Lie subalgebroids. So I take my Lie algebroid A, and I take a Lie subalgebroid, well, supported over the whole manifold. So a wide Lie subalgebroids. Okay, and the theorem is about integration of such objects. And okay, so the statement is that there is, well, I paraphrase it a bit, but there is a unique map. And now I will say what the various components are. So from some groupoid H min to my fixed groupoid, Lie groupoid G, where, so now I have to say what is what. So this H min is a Lie groupoid integrating B. So this is a Lie groupoid, well, integrating B. So, well, as you know, if you have a Lie subalgebroid of a Lie algebroid, it is itself a Lie algebroid. So it inherits the Lie algebra structure by restricting the bracket in the anchor. And, well, so this is a Lie groupoid integrating that Lie algebra structure. And so this phi is a Lie groupoid morphism. So Lie groupoid morphism integrating the inclusion. Integrating the inclusion of B into A. So B being a subalgebroid, well, the inclusion map is a Lie algebroid morphism. And, okay, and then there is a minimality statement. So any Lie groupoid morphism that integrates the inclusion factors through this map here. So we have a diagram of this sort. So factors as, so this is the, well, my given Lie algebroid morphism that integrates the inclusion. So in particular, so this Lie groupoid integrates B. And so that has to factor through the given, well, to the special one, so to say. H min. Yeah, I didn't give any name to this. So there is a surjective, well, Lie groupoid morphism, so that, like, the given map factors this way. Okay, so let me comment, well, briefly about it. Okay, so, well, not, I mean, there is something non-trivial, of course, about this theorem. Let's see. So, well, one key point is that we're looking at B not as an abstract Lie algebroid, but as a sub-object of an ambient Lie algebroid. And Okay, so what is this H min? Well, something you could do is certainly the following. Well, I assume that A is an integrable algebroid. Well, one can show that any Lie subalgebroid is also integrable, so you could take the source simply connected Lie groupoid integrating this. And by Lie's second theorem, that does have a map to G that integrates the inclusion. But there might be quotients of that source simply connected Lie groupoid that also come with a map to G that integrates the inclusion. But if you take an arbitrary integration of B, then, well, it will not come with such a map. So the statement is that there is a minimal one. Well, there is a special one, so a terminal object in a certain category. And, well, it's minimal in the sense that any other factors through it. No, very, very good point. So this is, well, so this map here is not injective in general. So if you work in the world of Lie groups, so basically if M is a point, then it is injective. So we learn in, I don't know, well, at the university at some point that for every Lie subalgebra, you have a Lie subgroup, which is in particular a subset of the original Lie group. So when M is a point, this is the Lie subgroup having as Lie algebra this. And in that case, the map is injective, but in general, it is not. So an example, well, maybe just orally, let's see. So if A is the tangent bundle, then, well, a widely subalgebroid is an involutive distribution. So those correspond to foliations by the Frobenius theorem. And this thing here is then the so-called holonomic groupoid of the foliation. And right, if you take G equal to the pair groupoid M cross M in that case. And yeah, in that case, the map is not injective usually. Okay, so I want to consider is a wider kind of, well, I want to learn some kind of singularities. So I will define what I call singular subalgebroids. And, well, at the end, I will get a picture that I will want to compare with this one. Okay, but so first, what are these objects? Well, okay, so these are objects that extend, well, the notion of wide Lie subalgebroid by getting rid of a constant rank condition. So this is in particular a vector subbundle, so it has constant rank, but, well, in many situations, we don't have objects that have a constant rank around. And so singular subalgebroid of A. So the definition is slightly algebraic, and I will also say where it comes from. So it's a sinfinity M submodule. I will always call it curly B. Submodule of what? Of the sections of A, let's say the compactly supported sections. There are reasons for this. And it should satisfy two properties. It should be finitely locally generated as a module, and it should be involutive. So if I take two elements that lie in this family B, their bracket should also be in B. Okay. So if any of you is familiar with, well, a certain notion of singular foliation that appear in the literature, for example, in the work of my collaborator in Scandalis, this is a straightforward extension where instead of looking at the tangent bundle as a Lie algebroid, you take an arbitrary Lie algebroid. So what this is yeah, so I have a family of sections. It's closed under addition and multiplication by functions. And yeah, as the module is locally near every point, it's finitely locally generated. It's finitely generated, so you have finitely many elements in here that generates the whole thing. And, well, involutivity, I think, it's a natural condition. Okay, so examples, well, motivating this. So two basic examples. So one is wide, well, Lie subalgebroids. So wide Lie subalgebroids. So this is the constant rank case. So how exactly, if I have a wide, well, let me just say list subalgebroid, it's simpler. If you have a list subalgebroid, then you can take its sections, so never mind this compactly supported, it's just a technicality, and well, and it will satisfy all these conditions here. And the other, well, basic example is singular foliations. So I didn't define exactly what it is, but well, I do it now by saying that it's the case A equal to Tm. So if you put Tm in this definition, you get what I mean by singular foliations. Okay. And okay, there are other classes of examples. So I will mention just one, the only one that will be a bit relevant for this talk, namely images of morphisms. So E and A are Lie algebroids. So let this be a Lie algebroid morphism. Let's say, over the identity. So these two are Lie algebroids over the same base and take a morphism over the identity. Then you can look, what can you do? Well, you could look at the image of this map, but that's usually not a well-behaved object. So the rank of the map, might vary. So what you get is not a subbundle of A as the image. What you can do is look at the image at the level of sections. Well, you can take this map at the level of sections and then look at the image of that. So you take sections of E and then images of such sections. So we get a family of sections of A. This is a singular subalgebroid of A. And okay, so in some cases, well, there are subbundles, there are Lie algebroids that do not admit Lie subalgebroids of a given rank. For example, if you take the tangent bundle to the two-sphere, it does not admit any, so the two-sphere doesn't admit any one-dimensional distribution. So, yeah?
So is this rank, is this number of generators some kind of two-point invariant, or what does it say something about?
Well, the number of generators, of local generators can vary, which is important. Well, yes, it is. It gives, so the local generators give you a bunch of things. I mean, so you ask about the number.
Yes.
So let's see. So once you have this kind of object, you can apply the anchor map of the Lie algebroid, and you get what I call singular foliation, which in particular gives you a partition of the underlying manifold into leaves. The number of generators at every point is an upper bound for the dimension of the leaf. But it doesn't need to coincide with the dimension of the leaf. That happens only at regular points. And so given such a thing, at every point there is an associated Lie algebra. Maybe I'll write it in a corner here. So for every point of M, you can take these objects. No, sorry, I have to change it a bit. So the elements of B vanishing at the point P, and you divide by the vanishing ideal of P, so the function's vanishing there, times B itself. This is a Lie algebra. And so, so I guess the number of the number of generators vanishing at P will be an upper bound for the dimension of this Lie algebra. Yeah. Yeah, sure, yes, yeah. I mean, it can be, it's not always the case. No. Let me think. No. So what you can do, you can do the following, but you lose information. So you have this family of sections, and at every point of the manifold, you can evaluate this family, right? And you will get a subspace of the fiber of the Lie algebroid at that point. And okay, so this will of course be a subset of the smooth sections of A that lie at every point inside that singular, I don't know how to call it, but it will not be all sections. It will not be all sections, just some of them. Okay, so let me go on. Okay. So, and now, okay, so actually, most of what I'm doing is directly inspired by the work of Andrew Dirac and Scandalis for singular foliations. And singular foliations are the simplest case, but well, I don't want to explain that case in particular today. So this result, well, what I will say now is certainly inspired by what they did. So the holonomy groupoid of a singular subalgebroid. Okay, so I'll state the result immediately. So let B be a singular subalgebroid of my algebroid A. So there exists a canonical map into G. So this will be a morphism of groupoids into G from some object that I will that I call like this in this way. So what is what? Okay, where? So this object that I call H, so it has some indices, sorry. So this is a groupoid over M. It's a diffeological groupoid. And I will say in 5 minutes what this means exactly, diffeological groupoid. And okay, well, about the map I cannot say much more than it's a map of diffeological groupoids. Okay, yeah. So, okay, so the main statement is that there is a canonical groupoid that you can associate to such a family of sections. I call it like this because it also depends on the choice of integration of A that I chose. That's what I call G. G is a Lie groupoid integrating A that I fixed. And so in this groupoid comes also with a groupoid morphism to G. And what kind of groupoids are these? Well, this was a Lie groupoid. This is not a Lie groupoid usually. Well, and that's not surprising. If it was a Lie groupoid, there would be a Lie algebroid around, right? But well, it is certainly a topological groupoid, but it has even a bit more structure that is tells you how to talk about smooth functions essentially. And okay, so I think I will not sketch the construction. So that's not my point, but I will say that it's a finite dimensional. One second, a finite dimensional construction. So you choose local generators of B. You look at some trivial vector bundle over a little piece of your manifold with a map to G, which is defined using these generators. Then there is a composition of such objects. You take the disjoint union of such objects divided by some equivalence relation, and that's how you define this groupoid. Okay. Yeah, I don't know if I really need that. It simplifies things, definitely. So the construction, for example, of this, of everything, also of this diffeological groupoid, uses the differential geometry of G. So I take sections of the Lie algebroid and then I extend them to right invariant vector fields. I take the flow. So working with the Lie groupoid makes things much easier. Yeah.
When you said disjoint union, this was a disjoint union of systems of generators at different points?
a disjoint union of, let's say, manifolds that are constructed out of generators at different points. Yes. Yeah. So I think, so your question, if I understood correctly, is what happens when this B is the image of the anchor map of some algebroid? Yes. Okay, so that will be a singular foliation, what I call singular foliation, right? And this will be, okay, so now you have to make a choice. You have to make a choice of Lie groupoid integrating the tangent bundle. If you take the pair groupoid, M cross N, then this recovers the so-called holonomic groupoid of Androuli-Dawkins and Skandalis, which for regular foliations is what you know as holonomic groupoid. Okay, so yeah, okay, so I will not say anything more about the idea. I mean about the construction, just that there is a canonical construction. But I think I should explain a bit the word diffeological, because probably it's not so well known. So the notion of diffeology goes back to Souriau in the 70s. And so let's take a set S. And diffeology is a family of maps into S. So let's call them chi into S, and the domain is some, well, ranges over open subsets of Rn for every n. So we don't fix n here, and n varies. So these are called, so this family, the elements of this family are called plots, and they satisfy some conditions, which I will list in a second. But first, maybe I should say the idea. Yeah, so this is supposed to tell you what are the smooth maps from open subset of Rn into your set. So you declare this to be the smooth maps. Well, into S. So the conditions are, well, that all constant maps should be here. So all constant maps are plots. And then, well, you want some, I mean, composition. You want compositions of smooth things to be smooth. So if you have a plot here, so this is open in some Rn, and if you take a C-infinity map in the usual sense from some other open subsets of some other Rn, then you want the composition to be a plot. And then there is a gluing property. So if you have a map into S and locally it is a plot, then the whole map is a plot. Okay, so these are not very strong conditions. So this is a quite relaxed notion of smoothness, which in particular doesn't allow you to talk about dimension. So the diffeological space does not have a well-defined dimension. And well, the good thing is that it's relatively easy to work with. And it seems to be sufficient for what I want to do. Okay, yeah, of course, manifolds are, well, are diffeological spaces. Well, you already know what it means for a map into a manifold to be smooth. And well, here I claim that this canonically defined groupoid is also a diffeological space. And that follows from the fact that, so its construction is, this is a quotient of a disjoint union of manifolds. Every connected component of this disjoint union has different dimension, but that doesn't matter. So the disjoint union is a diffeological space, and quotients of diffeological spaces are again diffeological spaces. So no matter how ugly they are from the topological point of view, they are always diffeological spaces. Okay, so let me make a couple of examples. Well, so one of them will just repeat the answer to the question to Alejandro. So these are the two basic examples of singular subalgebroids that I sketched earlier. So if I have a section of a Lie subalgebroid. Well, sorry, if I have a Lie subalgebroid defined over the whole manifold and I take its sections, then the canonical groupoid associated to it is the one that appeared in the theorem of Murdijk and Bursztyn. So this like minimal integration, so to say, of the Lie subalgebroid, which admits a map to G integrating the inclusion. And so this is as in Murdijk and Bursztyn. And well, okay, this is what is. Yes, of diffeological groupoids. Yes, yes. So in this case, the diffeological groupoid happens to be a Lie groupoid. So the manifold structure, induces the diffeology, as I just said, and it's that diffeology. And okay, so if B is a singular foliation, taking the pair groupoid, get, well, I'll write it quickly, the holonomic groupoid of Androulidakis Candalis. So they have long names. Scandalis, so the paper was published in 2009, I think. Well, and the construction here, so mimics really the construction. There are some technical difficulties because their building blocks are a manifold with two maps to the base manifold M. And so one has to interpret that as a map to the pair groupoid M cross M and then adjust everything. But in principle, it's an extension of the construction. Okay. So let me mention something here. So yeah, so they constructed their holonomic groupoid as in a way similar to what I did there. I mean, I took their work as inspiration, but there is an alternative construction of the holonomic groupoid of a singular foliation via paths. So paths in the sense of Lie algebroid paths, as in the work of Marius Kreinig and Rui Fernandez to integrate Lie algebroids. And this is by Garmendia, Alfonso Garmendia, and Joel Villatoro. And it was put in the archive last week. And Joel is somewhere there. Okay. And okay, so what about, well, being a manifold? So when is this canonically associated groupoid a manifold? So this groupoid is a Lie groupoid if and only if beta is projective, not beta, sorry, B is projective. In this sense, so if there exists a vector bundle such that beta is isomorphic as a C-infinity module to the sections of this vector bundle. So if my B is sections of a Lie subalgebroids, I'm in this situation, but there can be more general situations in which this happens. So okay, maybe the simplest example is if you take a manifold and you take a codimension 1 submanifold, then all vector fields on the manifold that are tangent to the submanifold, they're sections of a vector bundle. So they're a projective module. So that's called B tangent bundle. I'm not sure what you mean. So I'm assuming that E is integrable to G, integrates to G. So are you asking what happens if you remove this assumption?
I'm asking if you do the Kreinig-Fernandez quotient construction, is the Weinstein groupoid a diffeological groupoid? If it's not integrable,
Okay, so okay, now a couple of questions, well, which are natural, I think, at this point. Okay, so there is this canonical associated object, and well, getting it was some technical work, took well several years actually, but all the ideas were in the paper of Dirac Scandalis. However, so what remains unanswered from the paper is, can you recover well the singular subalgebroid, or at least the foliation, singular foliation in their case, from this groupoid? So does this have enough information to recover B? Well, you certainly expect that, but I mean, how does it happen exactly? And then, so this is the main question I want to address today. What is an integration of a singular subalgebroid? Well, there is this recipe that produces out of a singular subalgebroid a groupoid with a map. So you would want to call this integration, but well, what does it mean at all to be an integration? And okay, so what I will discuss now is the opposite. Well, is differentiation, which is supposed to be the opposite operation. So well, and that will well address both questions. So differentiation. Okay, so consider a morphism from H to G. So G is my fixed Lie groupoid. Well, let's say over the identity. Okay. Well, let's say so this is so H is a diffeological groupoid, and G a Lie groupoid. Okay. So well, okay. So why do I take this kind of data? To well, hope to differentiate to a singular subalgebroid, because that is what you get through this holonomic groupoid construction. And okay, so how so the objective now is to get in some canonical way a singular subalgebroid of the Lie algebroid of G out of this data. And well, so one can try like this. So this is certainly natural. So the formula are a bit ugly, but I will draw a picture. So this B lambda is a one parameter family of bisections of H. I will write it down in a moment. So you can take those, you can compose with the map, and then you can take the velocity times 0, d lambda times 0. So these B lambdas are a one parameter family of bisections of H. Okay, so that at time 0 we are at the identity. Okay, so okay, let me get back to this again. Okay, so first of all, to talk about this, I mean, so everything should be smooth, right? But smooth now in the world of diffeological manifolds, diffeological spaces. So, and to make sense of a smooth one parameter family, I do have to use the diffeological structure here. And so I apply this map. Well, this map is assumed to be smooth. So it will bring this family of bisections of H to a family of bisections of G. So I get a picture like, maybe I should draw it here. So if I draw the groupoid G like this, so this is a picture of the pair groupoid of the interval. Then so I have this, so each of these things here will be some bisection. So let's take an S fiber here. So you take, at time 0 you're here, so you take the velocity at every time. This was a bad color. And eventually you get a section of the Lie algebroid. So this thing here, this whole thing here is certainly contained in sections of the algebroid. Okay, so, well, this is a natural way, I guess, to try to associate, well, certainly a family of sections of the algebroid out of this data. But when does it satisfy the conditions that I imposed on singular subalgebroids, like involutivity, being locally finitely generated, etc.? That's what comes now. Let me erase the bottom here. So assume two conditions that I will not explain too much. A is holonomy-like, it's just a name. And B, okay, this is I will maybe explain it more orally. One parameter group. So the keyword here is group. So then B is a singular subalgebroid. Okay, well, and in that case, we say that this data here differentiate to B. That's the definition. So I think the question is whether, well, in these diffeological groupoids admit sections of the source or target map to every point. Well, in general, no. So this one does, yes. But if I pick an arbitrary one, it doesn't. So this is, I mean, the data that I started with here are very weak. I mean, if you wanted, you could, I think that's correct. I think you could take any abstract, like set theoretic Lie groupoid here, and put the stupid diffeology where the only maps are the constant maps. And well, from that, you cannot expect to recover much. That's why there are some conditions here that I don't want to explain too much in detail. First, because they're technical, and they might, maybe we can improve them. Yeah, that's the main reason. Probably you can improve them. So the second condition is, well, it's a bit embarrassing. So it says that what you get by taking the velocity of one parameter families of bisections is exactly what you get by taking the velocity of one parameter groups. So of course, this lies in here, but yeah, they don't have, it's not clear if they're equal. For Lie groupoids, they're equal, there's no problem. And this is a condition on the diffeological groupoid itself, which contains what Pedro said. So some conditions on the diffeology, on the generating set of plots, which implies that, for example, the source and target maps are open maps, and to every point you have sections. I mean, it's ugly, and I hope to improve it. But, well, it seems to work. And so rather than explaining the conditions, I want to tell you a couple of examples. And, well, okay, so like an example that has to be, well, something that has to be an example, otherwise I should have stopped with this project, is so this canonical diffeological groupoid with a map to G. So that's an example. And okay, so and if you have a Lie groupoid map, so assume that H is a Lie groupoid now, not just a diffeological groupoid, then these conditions are satisfied, and you get and this thing here is then the image of the map at the level of sections of the corresponding algebroid map. Okay. So I want to say two more things. That's why I'm not saying many details here. So integration, and we'll discuss some examples that, well, hopefully, will make clear how good or how bad this theory is. So integral. So now we define integration. Well, integration is pretty much the opposite of differentiation, but I want to add an extra condition. So an integral is, well, a map from some diffeological groupoid to G. So I mean morphism in the category of diffeological groupoids. over the identity such that, well, it should certainly differentiate in the sense that I just mentioned. Differentiate to B. And second, I don't want this to be too big. And so I want it to be as small as possible, so to say. So I require this map to be more or less injective in a neighborhood of the identity. So more precisely, so in a neighborhood H with a circle on top of the unit elements, the following happens. So if you have a bisection that goes to 0, not that goes to 0, but that becomes the identity bisection of G after you apply the map. So whenever you have such a bisection, then the bisection has to be the identity bisection itself. So this is not, this gets very close to saying that this map is injective near the set of units, but it's not exactly that. Okay. So now I have 10 minutes, I think. Well, 9. Okay, so for the examples, well, luckily what I really wanted to be an example is an example. So this canonical or diffeological groupoid with a map to G is an integral of B. So it allows to recover B through this procedure, taking bisections and velocities of families of bisections, but also it is, well, small enough. It is injective enough near the set of units. Okay, so to connect to the work of Bursztyn and Mordek, now I want to look at smooth, well, whatever. So let me call this smooth integrals. Okay, so a singular subalgebroid admits a smooth integral. So that means one that is a Lie groupoid. So i.e. so that H here, so that H is a Lie groupoid, well, and the map is a Lie groupoid map. So that happens if and only if B is projective. So projective meant that this module is isomorphic to sections of a vector bundle. Sometimes that vector bundle is well, subalgebroid of A, sometimes not. And okay. So if your model is not projective, which is a very nice condition, well, all integrals will not be, none of the integrals will be smooth. So in that case, I cannot compare with the work of Mordek and Bursztyn. So let's look at projective modules. So that was A. And then B, maybe I'll write it somewhere else. So if B is projective, then this canonical integration, so the holonomic groupoid is smooth, is a Lie groupoid. And all other smooth integrations are covers of it. So any smooth integral. So this is analog to the third part of the theorem of Mordek and Bursztyn. Factors as, so any other smooth integral factors through, like what this canonical one that are called phi. So this is a so this is a diagram of Lie groupoids. All errors are morphisms of Lie groupoids. So what this is saying is that this canonical integration, under the assumption that it is projective, is is minimal among all smooth integrations. And so a bit more explicitly the connection to Mordek and Bursztyn. So they consider only the case of Lie subalgebroids. So let's restrict to that. When B is a section of the sections of a wide Lie subalgebroid. So the smooth integrals. So the integrals, in the sense of the definition there, which happens to be Lie groupoids, are exactly those that appear in the statement of Mordek and Bursztyn. Are, well, I don't know, recover what I had in the third part of the statement about Mordek and Bursztyn. So they recover the Lie groupoids integrating the Lie subalgebroid, which admit a morphism to G integrating the inclusion. And okay, so okay, one can wonder, do you have, in this case, under this assumption that B is projective, are all integrals smooth or not? Well, and the answer is no, at least in the vast majority of cases. Well, okay, I phrased it as a remark. So the answer is usually no, because one can construct quite easily an integral that is not smooth. Sorry, the image of, so the canonical morphism from this, well, from the holonomic groupoid to G. So this was constructed in the first part of the talk. So with the quotient diffeology. So it's always an integral. So this holds for any singular subalgebroid, and typically it's not smooth. It is, well, at least usually not smooth, even when you assume nice things about B, even when B is a regular foliation. So in particular, well, in this case. So okay, so this case is the case where, well, we have a manifold, we have a regular foliation, and these are the vector fields that are tangent to the leaves. Then, so the image of this canonical map is exactly the equivalence relation. Well, if you take G equal to M cross M, so it's the equivalence relation given by the foliation. At the end, the foliation is an equivalence relation on the manifold that satisfies some smoothness properties, and well, the equivalence relation is belonging to the same leaf. Right? So that is typically not even an immersed submanifold of the product. So it is not smooth. And okay, so this provides examples of non-smooth integrals. And okay, so a key point here is that the equivalence relation, which we could write down, given a foliation we can write out immediately without going through all this work, has to be equipped with a special diffeology in order to be an integral. So in order to have enough information to recover, in order to have lots of information, which even in the singular case allows to recover the module. And the diffeology comes through by means of the holonomic groupoid. So the construction of the holonomic groupoid is really necessary in all this business. So let me, well, okay, I will not write down anything, but just say make one last comment. So what I said so far is basically that in the case of projective singular subalgebroids, where there are smooth integrations, the smooth integrations are what we knew earlier, but there are additional integrations that are not smooth. So what happens in the simplest possible case where we have a Lie group in a Lie algebra? So I have a Lie subalgebra of a Lie algebra. So that's so my B is the Lie subalgebra. So in that case, it turns out that under a reasonable assumption, all the integrals are smooth. And I have no idea if this assumption is always satisfied. The assumption says that if you take your diffeological group, well, if you take your integration, so that in particular this is a diffeological group, you take all smooth one-parameter groups in H, and you evaluate it at time 1, you obtain something that contains a neighborhood of the identity element. So this is saying something like the exponential map. The image of the exponential map contains an open neighborhood of the unit element. So if that condition is satisfied, then all integrals are smooth for the subalgebras of Lie algebras. And yeah, that's all.